Welcome, everybody. This is going to be part one of the Unit 6 presentation or lecture, if you will. I had already recorded this and then realized that I never shared my screen, and I had my camera muted on top of it. Also, it was just this little profile picture of myself for the whole duration of the presentation, so I apologize for that, and this is an attempt to correct that. Let's dig into the materials here. I'm going to not go into slideshow mode. I'm just going to pull the slides up in PowerPoint here and just kind of walk through them. This will take us up through slide number 39. Let's get a little legal disclaimers on the screen there. And then let's quickly kind of review what we were talking about in Unit 5, which was the data pre-processing part 1. We looked at basically how we extract features from models in NLP. We focused a lot on the bag of words model, the TF-IDF approach, and the word to vector model. This week, we're going to be looking at ways to analyze document similarity. And also we're going to talk about, what word vectors are, how to understand them, how to visualize them. And then we'll look at 3 different similarity analysis approaches, which are Cosine, Jaccard, and Euclidean, and how we use and implement those, and they each have their own approach. And then we'll talk about the search, cluster, and classify training data of LLMs. All right. First, we have to kind of define what document similarity is. And in essence, what it is it looks at 2 documents or 2 collections of text or whatever you want to, it could be something as short as a sentence or something as long as a novel, and then determines how similar those 2 documents are to each other, not only in what the words mean, but also the context of the words. And in order to do the analysis, we basically need to convert the words into vectors, or we need to, put them in a numeric format somehow in order to do the analysis with technology. And some of the metrics that we use are cosine, Jaccard, and Euclidean similarity techniques. We have to kind of review this concept a little bit of what word vectors actually are. And vectors are basically ways to plot textual information in the form of numeric value. Now, if you remember from our, other classes that we've had and other times that we've talked about vectors, that vectors are basically, you can think of them as a numeric value that has both a magnitude and a direction. And, we often represent this as an arrow, right? Because an arrow indicates direction, and the longer it is, the greater the magnitude. There's also kind of a direction associated with it as well. So like, which direction is it pointing? This way, that way, a little to the left, a little to the right, up, down, sideways, what's the direction of it? The vectors that we see here on the screen are pointing up into like what we call, the positive quadrant of a mathematical graph, right? The typical XY areas where X and Y are both positive, but it can actually point in other directions as well, right? And what they're, throwing out here as an activity, right, is and I assume they're missing the word you here. Can you identify the vector here, right? So in other words, we have the sentence, the football player was running 10 miles an hour towards the end zone. And how do we the point is, how do we turn this into a vector? Now, if you remember from some of our previous discussions, there are numerical ways to do that, to convert those words into vectors and then plot them, right? And give them, once they're turned into numerical vectors, the ability to process them numerically. Just to reiterate here, it says we know that vectors have both direction and magnitude, and then the graphs here represent vectors in the 2D and 3D space. And this is something we're going to start talking about, is the dimensionality. And I just want to kind of ground you on this right off the bat, and that is when we look at information predominantly on screens, we are looking at the information in a two-dimensional space. It's got like height and width, but it really doesn't have depth. Any attempt to represent depth on a two-dimensional surface is an approximation, and it's not really actually what it is, right? Um, and from a conceptual standpoint, we live, as bullet number 3 says, in a three-dimensional space. That's our existence. And in that space, we can determine depth because we get it because we're in that space, right? But on the screen, we're in 2 dimensions. And this is where it gets weird, right? Because when we start to do vectors, we sometimes exceed that three-dimensional space. In fact, vectors can go beyond 3 dimensions to 4, 5, how many can you even imagine? And all of those are considered valid dimensions, right? So here's an example of word vectors. So in other words, this one's a pretty simple one where it just simply indicates, does a word exist in a document or a snippet of text, right? And if it's a 1, it's a yes, and if it's a 0, it's a no. But when we look at the collective of all the words, like in a bag of words, for example, or the TF part, the term frequency part of TF IDF, we're just simply doing a count, right? Not all the words appear in all the sentences or all the documents, that type of thing. But we do come up with unique numerical representations of those. Now, we kind of go back to this and it says, we have this bag of words, we have a matrix full of numbers, and it says here we can say that we can't see them even though they are vectors because they are greater than three-dimensional. So in other words, I don't know how many words were on that page, maybe 10, 12 words. We're really looking at 12 dimensions. And that's, if 3 dimensions are hard to visualize in a two-dimensional space, how hard would 12 dimensions be to visualize? And that's kind of impossible, really. So what a lot of people have worked on over the years is to find a way to mathematically reduce the number of dimensions so that we have an approximation of the information in a lower dimensional space that still accurately represents that data, even though some of the details of it might be lost, but still accurately represents what it means. So here's an example on the left here of a traditional XY axis and a vector being plotted. And the vector is basically the combination of the X and the Y. And of course, the X and the Y determine the length. So like the bigger the X and the bigger the Y, the greater the length of the vector. And it does have a direction. It's starting at the origin point and moving towards that XY position, regardless of the angle. Now, if we add a third dimension, right? And this is the thing that we talk about a lot when we do like graphical programming and like we think about like 3D games and things like that, because the screen is 2 dimensions, but how do we represent the third dimension, which if we added it here would be a Z-axis, and in many cases that one is sometimes represented as kind of popping out from the screen or going down back into the screen. But what you're seeing on the right here is you're taking the X and the Y and they're kind of flipping it flat down and the Z is going up, right? And then they're drawing this other vector here that exists in 3-dimensional space. So it's not really on the plane of X and Y or the plane of Z and Y or the plane of X and Z. It's somewhere in the middle of all that in 3-dimensional space. And this is just a crude representation of it, the best we can do in a 2-dimensional surface of the screen. So you can see the challenge here, right? Now start to add in more dimensions, and how do you even begin to visualize something that complex? It is really kind of pretty deep. What I would encourage you to do is follow this link here, and they kind of go into this whole concept of dimensionality, dimension reductions, and just kind of this is a concept. You can think of dimensions in many different ways. So some people think of like, okay, we live in a 3-dimensional space and time is maybe the 4th dimension, although there's debate about that too. And then maybe spirituality is the 5th dimension. And then who knows where it goes from there, right? And those are all crude representations of three-dimensional beings trying to talk about higher dimensional spaces that they really don't get, right? Because why? Because we don't live in them. We can get 2D and 3D, no problem, because, well, 2D flat on a screen is easy, and 3D is the space we live in. So it makes sense to us. And now they start posing these questions, and I guess I've been posing them all along as I do this. And it says, imagine we're living in a different dimension for a moment. What might it be like? How would it be difficult to imagine that space? It would be very, very difficult because it's not what we call normal, right? So in order to make it kind of work, we sometimes take that complexity of the higher dimensions and reduce them mathematically so we can start to visualize higher dimensional objects in lower dimensional space. So they start with this example here, and this is kind of a crude example, frankly, but they have a picture of a ball, which is a 3D object, right? Now, I don't have to see the backside of that ball to kind of imagine what the backside might look like. It probably looks kind of like the front, right? Probably the same color pattern keeps going. It feels like it's three-dimensional because you see the curve of it. You also see kind of the light playing upon the surface, right? And one way that I could reduce some of the information in that image is, well, I could take away the color, right? Now it's still, I can still kind of see light and shadow though, so it still kind of sort of looks like a three-dimensional object. But really, if I take a sphere and reduce it to a two-dimensional object, it ends up in a two-dimensional space looking like a circle. That's the whole point. And really, even though the image on the left has an appearance of dimensionality to it, it really is just a circle, right? Regardless of what the surface is trying to deceive your eye into thinking that it's three-dimensional. And so they have this kind of thing, right? So how do you transform that object from the higher dimensional space to a lower one? You kind of make a visual representation that kind of holds the basic, features of it. Like basically, in this case, it's size, right? It is maintained. But we do lose information about the ball as we reduce that dimensionality, because that circle certainly doesn't contain all the same information as the image on the left, right? Even though that's still a two-dimensional object. But they pose a kind of an interesting question here. Who's to say that ball's not a sphere cut in half and you're just not seeing the back half of it? So maybe if I grabbed that ball and flipped it around, it's cut off, right? I mean, that's a possibility. We really don't know, right? So we're guessing. So all that extra information that's on the other side, we don't really know if it's there or not anyhow, right? And that's kind of an interesting thought. Now, they give this kind of neat little walkthrough here of like how dimensionality reduction happens. So like on the image on the left here, we see an attempt once again to plot three dimensions in a two-dimensional space. And what they're trying to represent is that we have two cylinders, right? And the cylinder is basically two circles that are connected. Think of like a can of soda or something like that, right? That's a cylinder. And that cylinder has, kind of like the two ends of it, and then it has a round shaped connector between those two circles on the end, right? And we can kind of sort of represent that hypothetically as a three-dimensional object here, and we can kind of visualize that. It's like, okay, yeah, I get it. That's kind of like a can, right? But if I remove one of the dimensions, so if I boil it down to just two of the dimensions in this case, I might end up with an image that looks like this. And I want you to notice that this is on the Y and the X axis. So like if I took those cans and they're sitting on the table and then I'm just looking at them from the top, right? What might it look like? Well, all I would see is two circles if I could get exactly above them, right? And so that's one dimensionality reduction that could happen. Another one is as you look at the other dimensions of Y and Z, right? Where I'm flipping the graph to, two different axes, right? And from that perspective, all I'm seeing is a line because the circles above, right? If I flip them in three-dimensional space by 90 degrees, I would just see a line, and then that line represents the circle, and the circle represents the cylinder, right? And so this is an example of dimensionality reduction. Now, the information is still kind of there relative to those two axes, but it's certainly visually much different than what we originally started with. However, we can still use that information to do processing and analysis, right? So for example, we can look at those two lines and go, yeah, they're pretty similar, right? They're about the same length. And in fact, these two circles are about the same size. In reality, the depth of the object is deeper, but it is true that they might have the same circumference and diameter, right? And then if I just look at a slice of the top of each of them, yeah, those are both similar also. So there's aspects of them that are similar, and we can analyze that because of it, right? So this is kind of the maneuver here. Now, when we take word vectors and we start to plot them on a graph, right? And this is an example you can see of like words all related to either beverages or food. And you plot them here, right? Notice we have different colors, right? And all of them are a different distance from the origin point in the center, and they're at a different angle relative to the the origin point. And those are kind of how word vectors are put together. Now, there is this interesting website here, and I'm not going to demonstrate it in the video, but I would encourage you guys to click on that link and follow through. And this, I think I set this as an extra credit assignment, so that's kind of why I'm not really doing it here. You guys can explore this on your own. I think we may have looked at this tool also in the first AI class, if I remember correctly. But basically what they're pointing out is if we have, keep in mind, a model that we build around word vectors. So let's take this all a step further. We start with text, we convert the text to some sort of a numerical format, a vector, right? And now we can analyze that vector. And not only that, we can drop it into a neural network and start mapping out the nodes and all the possible connections between them and all the pathways that are possible. And then we train our model, and we end up creating this visualization as a result of all of it. But notice how like these pathways in the neural network here, right? Like some are blue, right? And some are red. And then like, for example, the orange or the red one here, eat, is following this pathway, which goes to apple. So it doesn't make sense to eat an apple. And here's another pathway that kind of leads to the same thing, or eat an orange and eat rice. But it might not make sense following another pathway, whatever, whatever the derivation is. The tool that this links to will walk you through kind of like playing with some of their models. Like they have these little drop downs that you can kind of go through. Okay, so play with the tool, try to retrain the model, play with some of the different settings, and you can watch the model evolve. This is like a free online tool, which is pretty neat to play with. And like kind of the point is, right, and this is what the control panel looks like on the website, by the way, is you're given some stuff that is preset. So if you click this little drop down thing here, there's different models that are pre-built that you can pull up and play with. They have some of the settings, the configuration settings in the background, probably driven by Python. We don't really know, but that's the assumption here. And then you can watch it train on that data, and then you can also control a lot of the settings, right? So what's interesting about it is this is the dimensionality reduction tool, the PCA piece of it. So be sure to try that. So the basic activity is this, right? And this is the thing that you will kind of do as an extra credit activity, if I remember right, is to load the king and queen preset, force it to run 1,000 iterations, click on the PCA button, which reduces the dimension, and then look in at the scatter plot that's created, and then follow these steps here to basically do the work. You will get some outputs that kind of look like this. And then you'll notice like this is one that we've talked about before, where there's man and woman and king and queen. And what are the correlating pieces there? Are, like man and woman as words are kind of similar, right? Because they're like opposite genders. And then king and queen are royals, but that's also got a gender to it as well. So I could be grouping really man and king and woman and queen, right? I probably wouldn't group man and queen and woman and king, if you get my drift, right? Although some people might try. Uh, but it is a thing, right? I mean, so it's like different types of similarities that you're finding in language. So kind of the big takeaway basically is you convert your words into numbers, right? Vectors, basically. The vectors often go well beyond 3D space, so we can't mentally visualize it or even electronically visualize it. So we do dimensionality reduction, and then not everything can necessarily be analyzed, right? Because we are losing some data. So, for example, if I wanted to look at that cylinder from the previous slide, like the body of the cylinder, well, that's not happening because I'm reducing it down to either the circle or the line, right? So the can part of it is kind of gone, right? So I can't really analyze that. But I can analyze the tops of the cans and the sides of the cans. This is really kind of the point of it, right? So we're still finding similarities, right? And this is how some of this natural language processing works. Now we can use, the vectors then to figure out similarity aspects using a number of different mathematical techniques. So the three primary ones that we use are cosine similarity, Jaccard similarity, and Euclidean similarity, and they all work a little bit differently. What I'm going to start with here is talking first a little bit about the cosine similarity. And I'm going to take us up through slide 39, and then you'll switch over to the part two of the lecture, by the way. But cosine similarity is really kind of a metric that extends from, your traditional Pythagorean theorem, where you have sine and cosine and tangents and stuff like that you learn about usually in geometry class or trigonometry class, typically. But basically, what a cosine does is it measures the angle between two vectors. Like whatever vectors I generate, what's the angle in between them? The less the angle, or like this, the more the vectors are pointed in the same direction and not very far apart, the higher the similarity. So that's one measure. And you can actually click through this link, and I would encourage you to do that and read through where they talk about this process in much more significant detail. It's pretty well written. I very strongly suggest that you read it. And they do kind of plot things here, right? So like if I have things that are really similar, the vectors might plot like this. They're really close. They're in the same quadrant. I might also have things that are unrelated, so like, all right, this one's over in that quadrant, this one's over in this quadrant. They're not really very related. And then I might have things that are complete opposites. They're not only not related, but they're inverse meanings of each other, right? And then they show like basically the numeric values that might be assigned. So like if the angles are really similar, in fact, if they're exact, the value is 1 or 100%, but usually it'll be a little less than that. If they're unrelated, we'll get a 0, right? They can't really be related because they're in different quadrants. And then if it's in the opposite quadrant, then you get like the negative percentage or the negative ranking. Well, when you use this tool to try to find relationships between language, I want you to look at all the different things here and notice how many of these words could be grouped together in similarity, right? And once again, I'm going to just kind of explain that depending on how you look at it, you can find different types of similarity, right? So for example, if we look at she and he, those are pronouns, right? So they're similar because they're pronouns, even though they're opposite genders. Man and woman are words describing gender, once again, similar in, let's say, value, but pointing out opposite meanings or opposite genders. Same with male and female, same with king and queen, right? And which one of these are more prominent is relative, right? One person might say, well, king and queen are more prominent, they're more important people. That's arguable, I guess. But there's also the correlation that she, woman, female, and queen are also similar because they all refer to the same gender. So they have a gender similarity as opposed to like, being a pronoun or a noun or a formal noun, right? All that kind of things. So how do you group those? Well, you can group them in a number of different ways. It depends on which aspect of the dimension you're looking at, if you feel what I mean. Now, truly, this could be at maybe at least 3 or 4 or 5 or 6 or 7 or 8 dimensions that you could compare in different ways, depending on how you want to analyze it. So this is the kind of analysis that we can do with that. Are they similar in a certain way? Like, are they both pronouns or are they more formal ones, right? Are they the same gender reference, for example? And so this is a very useful tool. And here's some thoughts that are kind of related to this and might help to clarify how this might be used. It says, for example, a chatbot might take a question and search through its knowledge database, finding a piece of information that is most similar to the question and giving that information as its answer. And so you might throw a keyword into a chatbot, and maybe the keyword is, I don't know, you're calling Spectrum because your internet's down, and you're hitting the chatbot, and and you might say internet not working, or Wi-Fi down, or something like that. But it's going to correlate it to like, oh, you're having a problem with your connection, and it's not working, in some capacity. And then it might, give you a standard response. Have you tried rebooting your router? For example, that might be its standard response right before it takes you to the next level of support. So how do they figure that out? Well, they kind of have to give value to those words. So they're going to be looking for certain words, right? And how much different would that be if you get to the chat bot and you say, can I just talk to a person or agent or whatever you say, which is a whole lot different than internet is down, right? Or not working. So here's kind of the thing, right? Is that like, if you're talking to a chat bot, is that predefined? The answer is probably. Or is it dynamically looking at the words that you're typing, comparing them to things, and then looking for the answer? I think that's probably less likely with most chatbots, but that could be the case, right? It certainly is the case when you're using a generative AI engine. And when it finds those similarities, is the computer really comparing ideas here? That's the other question you should ask yourself. Or is it just finding similarities in the words based on certain context and meaning? And that's really what we're driving towards here. All right, this is going to end the first part of the PowerPoint. When you get to the second one, it will start on the slide and carry you through the rest. All right, so this video ends here, folks.